Hello everyone. In this video we are going to be looking at introduction to motion, particularly motion in one dimension. So what is the meaning of motion? Basically, when we look at any object for observation from the physics point of view, we either say this is at rest or we say this is in motion. So these are called as two states of the object. So either the object will be at rest or it is going to be in motion. Now what do you mean by rest? So if you look at every object, it will have a position, like in an coordinate system. Say we have an horizon and we have the x-axis, we have the y-axis, we have the z-axis. We call it as the Cartesian coordinate system. We can look at the position of the particle as the x coordinate value, y coordinate value, and then z coordinate value. So this combination will represent the position or the location of the particle. We can even represent this with a vector which we call as the position vector. Now if the position of the particle is not changing with the time, then that is supposed to be rest. If the position of the particle is changing with time, then we say the particular particle is in motion. Now when we talk about the rest and motion, after all, these two are relative terms. I'll give an example as to why I am saying that these two are relative. Let us say, for example, there is an object A which is moving towards the right side, and a person B who is at rest or who is standing on the ground will see that the object A is actually moving, and we have another object C which is moving along with A in the same manner. Then we say that at whatever time that C is observing, A appears to be at the same position or same place. Now we can think about it in different ways. Like say for example, we are moving in a train, and so we are sitting in a particular chair, and we see the next person who is sitting adjacent to us. For us, he is at rest. Whereas if you try to see it from a person standing on the ground, so he will see that this person is in motion. So the idea of motion and rest are relative. They depend upon the observer. So we'll talk about this in detail when we go to the concept of what is relative motion. But here, whenever we talk about generally motion or rest, we are understanding that the observer is not moving. So we always talk about the rest and motion with respect to an observer or frame of reference. Rather, we call it as the frame of reference. Here that we are considering is supposed to be at rest. So with respect to this frame of reference, we are trying to say whether the object is in motion or whether the object is at rest. So rest is when the position is not changing with time, and motion when the position of the object is changing with time. So these are the two states of any object or particle in terms of the observation. Now we have been using the word object and particle, but we may get some kind of an misunderstanding as if what is this object and what is this particle. Now for a lot of time in this mechanics, we are going to be treating objects as point masses. Now when I say that the location of the particle is a particular value for the x coordinate, y coordinate, z coordinate. Let's say I'm saying the particle is located at 1, 1, 3. It itself means that we are referring to an point mass which is located at exactly one single location. And normally when we talk about the objects are actually distributed masses. Means they'll be occupying some volume. They will not be located at a particular location. So for most of the part of mechanics, we are going to be dealing with the point masses which will be located at a single point. And when we go to the rigid body motion, we are going to be talking about the motion of these distributed objects. Now moving on to the idea of how do we go about measuring the motion. So let us say a particle is changing its position with time. Now how do we quantify this change? Because in physics, after all, we'll be interested in measuring the things. So one of the parameters which can be used to measure this motion is what we call as distance. So what is this distance? So let's say, for example, a person is starting from point A and then he is taking a path to reach finally B. The total length of the path covered by this particular person is basically what we call as the distance. And of course, the SI unit of this will be meter. If you talk about the dimensional formula, it will be L. So distance is a parameter to measure the motion of the object. Now distance, since we are only talking about the length, it is a scalar quantity. It just has value and there is no direction associated with it. And we can see one thing, the distance will depend upon the path taken, which means to reach from A to B, I can take different paths. Now as the path changes, the value of the distance also will be changing. So this is about the distance which is used to measure the motion. We have another parameter that is also used to measure the motion, which is called as displacement. Now we'll try to understand what is the exact difference between the two. Now I'll go with the same case of moving from point A to point B through a particular path. So this is the path taken. Now irrespective of the path taken from A to B, if we try to just measure what is the straight line distance, or I can say the shortest distance, which will be of course the straight line distance from A to B. So when I say A to B, we are talking about from initial point to final point. This will give the value or the magnitude. Now why we say magnitude is because the displacement is defined as a vector quantity. So the shortest distance between the initial point and final point will give the magnitude of the displacement, and direction of the displacement is given from initial point to final point. So that will give the direction of the displacement. So this is about what we call as displacement. Now as we can see, displacement will be independent of the path taken. It only depends upon what is the initial point and the final point. So displacement is also measured as shortest distance. So the dimensional formula will be L and the SI unit will be meter. When we talk about the motion of any object, we can either measure the motion by using distance, or we can measure it by using displacement. After a while we will see that there is going to be more importance for displacement, since it is a vector and also it is related to some of the other parameters of motion like velocity and acceleration. Let's look at this illustrative problem which will try to make the concept of displacement and distance clear to us. So we have a person who is moving 4 meters along east, and then he is changing the direction to move 3 meters along north. We need to find what is the total distance covered and what is the displacement. So we have the east and north directions being mentioned, and usually whenever we talk about the directions, the convention that we will be following is we'll take the right side to be east, and or rather so in a 2D plane, because we are usually comfortable with the x and y axis kind of a system. So we take the positive x-axis to be the east and positive y to be the north, negative x-axis to be the west, and negative y-axis to be the south. So why we are using this is basically to have a certain a standardized way of representing these directions, because very often we will be having problems where there will be directions being mentioned. So let's say for example I am starting from point A. So we are moving 4 meters along east to reach point B, and then 3 meters along north to reach point C. Now when we talk about the distance is nothing but total length of the path covered, which will be 4 meters plus 3 meters. It is going to be 7 meters. When we want to talk about the displacement is a vector. So we can even represent this with a bar above. Displacement will have both magnitude as well as direction. Now the magnitude of the displacement will be given by the straight line distance from A to C, which is nothing but the length of the hypotenuse. Hypotenuse length in a right angle triangle, we can get it by using the Pythagoras theorem. It will be root of base square plus height square, which will be root 16 plus 9 root 25, which will be equal to simply 5 units. Here the system is meters, so it will be 5 meters. So the magnitude of the displacement is 5 meters, and the direction will be from A to C, because the direction of the displacement will be from initial point to the final point. We'll look at one more example. Let us say we have an object which is moving from A to B along a circular path. So which means the object is moving from A to B along this particular circular path of radius 14 centimeters. And here, as we can see, this is actually not covering a full circle. It is covering a circular arc of angle 60 degrees. We need to find what is the distance covered and what is the displacement. As we know, distance covered here will be the length of the arc. So distance is going to be the arc length. We have a formula for the arc length. So in a circle, length of the arc will be equal to r into theta, where r represents radius and theta is the angle which is made by the arc at the center of the circle in radians. So here the value of the radius is 14 centimeters into theta here is given as 60 degrees. So if you want to convert this into radians, we have to multiply with pi by 180, because the method to convert angle from degrees to radians is multiplying by pi by 180. So 61s are 63s are. So 60 degrees will be equal to pi by 3 radians, means pi by 3. So here we can take the value of pi to be equal to 22 by 7, because we see that 14 is a multiple of 7. So finally what we'll be having is 44 by 3 meters. So this is about the distance covered. If you want, we can even get the value in the decimal places. Now let us talk about the displacement. So displacement is shortest distance from initial point to the final point. Means we have to draw a straight line from A to B. Of course, the direction of the displacement will be from the initial point A to the final point B. So let us focus on getting the magnitude of it. Now the information that is available with us is radius of the circular arc is 14 centimeters and the angle over here is 60. The only way in which we can get the particular length, straight line length from A to B is by using some property of the triangle. As we can see, there is a triangle over here that is getting formed. Let us say O is the center of the circle, and we can see this triangle OAB which we are observing. O is equal to OB, because both are radius, which means the angle opposite to OA and the angle opposite to OB, which we can call it as simply angle A and angle B, they both must be equal, because in a triangle when two sides are equal, the opposite angles also are going to be equal. But already we have angle A plus angle B plus 60, because in triangle OAB sum of all the angles will be equal to 180, which means angle A plus angle B is equal to 120 by taking the 60 to the other side. This implies that both angle A and angle B must be equal to 60 each. If these two are also 60, then we see that there is one interesting thing happening here. The triangle OAB is actually becoming an equilateral triangle, because all the angles are equal. It's an equilateral triangle. Now if it's an equilateral triangle, all the side length also must be equal. Since OA is equal to OB is equal to 14 centimeters, the value of this AB should also be equal to 14 centimeters. Now sometimes, right, when we are solving these distance and displacement problems, we may have to use the properties of triangles or properties of quadrilaterals, or even sometimes circle properties. So it's good that we are getting some practice on this. And when we looked at both the examples, if we try to exactly measure the values, we would have observed that the distance value in both the examples is always more than the displacement magnitude. I'm talking only about the two examples that we have looked at. In general, whenever a particle is moving from one place to other place, let us say we look at this as the path. So this is the total distance covered, and displacement is nothing but the shortest distance from A to B. We see that the distance covered will be always more than or equal to the magnitude of the displacement. Now when the two will be equal is if, say for example, a particle is moving from A to B along a straight line path without changing the direction. Now why we are mentioning without changing direction is because even if it is moving in a straight line, if there is a change in direction, then the distance covered and the displacement magnitude, they both will be different. So just to tell you an example, let us say a particle is going from A to B, and then it's still moving along a straight line. It comes from B to C. This is the final point. This is the initial and this is the final. The particle is still moving along a straight line, because when a particle is moving along a straight line, we can have two possible directions of motion. So as we see, the distance covered here will be equal to AB plus BC, whereas when we talk about the displacement magnitude, we will only be looking at the shortest distance between initial point to final point, which is nothing but AC. So that is the reason why the only case where distance is equal to the displacement magnitude is when the particle is going in a straight line without changing the direction. If we see that the object is already in motion, then comes the aspect of comparing the motion. Comparison will only arise when we at least have two objects moving. So let us say we have an object which is in motion and object B which is also in motion. Now we can compare the motion of the two objects by looking at what is the rate at which they are covering the distance. Means we can measure what is the distance covered by the object per a given time, and that is what we will be measuring as speed. So since distance is a scalar, speed is also a scalar, and the SI unit of this will be meter per second, which is nothing but the SI unit of distance divided by the SI unit of time, and the dimensional formula will be L t to the power of -1. So whenever we want to compare the motion of two objects, we can use speed. So an object covering more distance in a given time is supposed to have a higher speed. An object covering lesser distance in a given time is supposed to have a lesser speed. Just like the way we have speed defined in relation to the distance, we have another term that is used to compare the motion of two objects, which is called as velocity. And velocity is a vector which is related to the displacement. So the velocity will be displacement of the object divided by the time taken. Since it is related to the displacement, velocity is a vector quantity, and this is another parameter that is used to compare the motion of the two objects. In terms of the unit will be still meter per second, and dimensional formula will be same as the dimensional formula for the speed. The difference being the speed and velocity Speed is a scalar and velocity is a vector. If you look at the comparison between the two, we see that since, as we already talked about it, the speed is distance by time, it will be always more than or equal to the magnitude of displacement by the time taken. Why? Because in the previous formula which we had, distance always more than or equal to the magnitude of the displacement, we just divide both sides by time, and over here we are getting speed which will be always more than or equal to the magnitude of the velocity. So this is about the relation between the speed and the velocity. Now both these things are used to compare the motion of the object. The velocity is also defined by using the concept of position vector. Let us say we are talking about a particular coordinate system where so usually we will be referring to the Cartesian coordinate system. So in mathematics you will also study that there is one more coordinate system called as the radial coordinate system. So let us say the initial position vector of the particular particle is RA, and it is going to final location B. As it is moving from A to B, the position vector is RB. Now the displacement, which is a vector, so from initial point to the final point, displacement S bar will be given by, so as we can see from the properties of the vector addition, RA bar plus S bar is equal to RB bar, which means S bar will be equal to RB bar minus RA bar. This is also represented as delta R bar, change in the position vector, which means final position vector minus initial position vector. So this will be the displacement. So velocity, which is shown as V bar, is also represented as the change in the position vector divided by the time taken. So time taken, either we represent it by T or we can even indicate this with delta T. So this is about the idea of speed and velocity. Now we look at one illustration question to understand how this speed and velocity will be defined in a particular motion. Let us say we have a person who is completing one full circular motion or one full circular rotation along the perimeter of a circle having radius 21 meters in 10 seconds. So we need to find what is his speed and what is his velocity during this particular journey. So we have a person starting from a particular point, he is going along a full circle and then coming back to the same point. Now when we talk about the distance covered here will be the total perimeter length, which is equal to 2 pi r. So 2 into, in case of pi we can take it as 22 by 7 into r value, radius of the circle is given as 21 meters. So 7 ones are, 7 threes are. So what we have is 44 into 3, which is equal to 4 threes are 12 and 132 meters. This is the distance covered. So speed is defined as the distance covered by the time taken divided by 10 seconds, which will be equal to 13.2 meter per second. This is the speed. Now when we talk about the displacement, of course it is a vector, but let's just look at what is the displacement magnitude. When the particle is completing one full rotation, whatever is the initial point is becoming the final point, which means the shortest distance between the initial and final point will be 0. So if in any motion the particle is coming back to the starting point, the overall displacement will be equal to 0. If the overall displacement is equal to 0, then the velocity will also be equal to 0. So here, of course, for vectors which are having 0 magnitude, we call them as null vectors. The direction has not much significance. So this is about the way we'll be able to find the speed and the velocity in a given journey. So if we look at this, right, we want to confirm whether there is motion or not. Distance is a better parameter to confirm whether there is motion or not, because if the body is moving, then definitely there will be a non-zero value for the distance covered. But even if the object is moving, if the initial point is equal to final point, then we see that the displacement is 0, and we will not be able to confirm whether there is motion or not. So if the object is really not moving, then displacement will be 0. Even if the object is moving and initial point is equal to final point, in that case all the displacement will be equal to 0. Now what we observed in the previous example is we are trying to look at what is the total distance covered by the object in the journey time. Now what happens is, even if you take for example a person taking a 100-meter sprint, let us say he is completing it in 10 seconds. We'll just try to focus on what is his speed for the journey. So his speed for the journey will be, he is covering a total distance of 100 meter divided by the time is 10 seconds, so we'll get 10 meter per second, which means what we're expecting is for every 1 second of the journey he'll be covering 10 meters. So if you break the journey into, say for example 10 intervals, each 1 second, what we are anticipating is he will be covering 10 meters in each of these parts, which does not happen practically. In the first second, from t is equal to 0 to t is equal to 1, this is what we call as the first second of the journey, he may only cover probably 3 meters. In the second second of the journey, he may cover some 6 meters, which means if you try to find the value of speed in the first second of journey, it will be coming as 3 meter by 10 seconds, which is equal to 0.3 meter per second only. If you go to, say for example, the last second of the journey, which is t is equal to 9 to t is equal to 10, he may cover a distance of even some 16 meters, which means his speed in this will be coming as 1.6 meter per second. Now the thing that we are trying to understand over here is the motion of the particle in the entire journey may not be having a constant value of speed. It may keep on changing. Further, even if I break the first 1 second interval into two parts, first t is equal to 0 to t is equal to 0.5 seconds and t is equal to 0.5 seconds to t is equal to 1 second. It is not like he is going to travel 1.5 meters here and 1.5 meters here. Maybe in the first half second he may cover only 1 meter. The next half second he may cover 2 meters. Thereby the total value is becoming as 3 meters. So what we would be looking at to compare the motion of two objects at a particular instant of time is what we call as the instantaneous value of the speed. Now the instantaneous value of speed, and also we'll talk about the instantaneous value of the velocity, are the parameters which are used to compare the motion of two objects at a given instant. Now how do we go about defining them? So we'll define both of them in a similar manner. So we have the speed and we have the velocity. Now we take a time interval which in the language of mathematics we call as differentially small time dt, and in this small interval, let us say the distance covered by the particular particle is ds. It is a very small distance. If we try to divide the distance covered in this small interval divided by the interval value, which is what we call as the differentiation, this will give us what is the instantaneous speed. Now how we will get this value is either by using the differentiation method or by using the graphical method. So we'll talk about this particularly when we go to the the 1D motion in detail, but here we just need to understand that we can have another term which is used to compare the motion of two objects, which is the instantaneous speed, other than the average value. So when we do total distance by total time taken, which can be done simply by using the division operation, so we will only be able to get the average speed. So what we have talked about in the previous definition, total distance by total time taken, is only giving us the average speed. So this will give us what we call as the instantaneous speed. Now how we'll get this differentiation operation? Already we have discussed this in the basic mathematical tools. So what we do is, if we look at the distance covered as delta s and the time interval is delta t, we take the ratio of the two, and we will use the concept of limit in mathematics, where the delta t is made to approach 0, and this will give us the value of the ds by dt, small displacement in the time interval dt. So we'll talk about this, how we'll use this particular operation in a little later, but this is basically what we call as the instantaneous speed. So instantaneous speed is a better measurement to compare the motion of two objects at a given instant. Similar to the instantaneous speed, we can also define instantaneous velocity. So we take a very small time interval, and in that small time interval, let us say the displacement is ds bar. So we are using the vector notation, and already we have seen that displacement can also be given as change in the position vector. So if you take ratio of or the division of the small displacement by the time interval, which we can also write it as the small change in the position vector by the time interval, this will give us the instantaneous velocity. Now in the same way, we will be able to find this value by using the differentiation method or by using the graphical method. So these are the two parameters which we call them as the instantaneous parameters. And if you observe the motion of an body, it might so happen that the velocity of the object might change with time. Now we will be understanding what is the reason why the velocity of the object is changing when we go to the laws of motion. But just to give you some idea, one of the popular laws of motion is, if we have an object which is in motion or an object which is at rest, it will continue to be in the same state unless there is an external force acting on it. That is what we call as Newton's first law or Newton's law of inertia. So if you have an object which is having a particular velocity, it will keep on going with the velocity unless there is some external force acting on it. But if there is an external force acting on the object, then we see that the state of the object can be changed. Means the velocity might be increasing or velocity might be decreasing. So if the velocity of the object is changing, then the rate of change of velocity is what will be measured as another parameter for the motion, which is called as acceleration. So acceleration is defined as rate of change of velocity. Now the way we talked about the average and instantaneous values, here also we can talk about the average as well as the instantaneous values. So what do we mean by this? If you look at the finite time interval delta t of the journey, let us say initial velocity is u bar. So we are always trying to represent the vector notation, and the final velocity is v bar. Then acceleration will be change in velocity, final velocity minus initial velocity by the time taken. This acceleration is what we call as the average acceleration, because this is measured for the total time of the journey. If you want to understand how the the velocity is changing at a given instant of time, so then we have instantaneous acceleration, which is measured as, we take a small time interval dt and then we see what is the change in the velocity in that. That is also going to be very small value. The ratio of dv bar by dt will give us what is the instantaneous acceleration. Now this also is estimated by using either the differentiation method or by using the graphical method. So when the object is changing its velocity, then we can talk about both average acceleration as well as instantaneous acceleration. We'll see that this acceleration is related to the force acting on the object. So when we go to the Newton's laws, one of the other important laws of the motion is the second law of motion, which will relate the force acting on the object to the acceleration generated in it. Now we broadly understood what are the parameters that are used to study the motion. So we talked about speed, we talked about velocity, and we talked about acceleration. So generally, when we are going to study the motion of objects in this one dimension or even two dimension as well as three dimension, so we look at these following standard types of motion. If the speed of the object is a constant, then we will call it as a uniform speed motion. If the velocity of the object is constant in a particular motion, then we will call it as uniform velocity motion. If the acceleration is constant, then we will call it as uniform acceleration motion. So this is an important type of motion that we'll be studying. And if the acceleration is changing, or we say it is variable, then we will call it as non-uniform acceleration motion. Now for this uniform acceleration motion case, we have what we call as famously the equations of motion, which are nothing but the relations between the different parameters used to measure the motion. And the non-uniform acceleration motion problems are usually solved either by using the graphical methods or differentiation and integration methods. So we'll take a look at it when we go to the particular sections, but these are the broad types of motion that we are going to be discussing. Now the study of motion, as we are dividing the topic names itself, we are going to be doing under this 1D, 2D and then 3 dimension. What is the one-dimensional motion? If the motion is confined to a straight line, that is what we call as an one-dimensional motion. And when we are confining ourselves to motion in a straight line, we will be looking at the coordinate or the position of the particle, which is going to change with time, will be only one value. Means if say for example the object is moving along the x-axis, only the x coordinate or the x position value will be changing with time. If it is moving along the y-axis, means only that value will be changing. If it is moving along the z-axis, means only that value will be changing. So the position or the coordinate, only one parameter will be changing. The examples of this can be if you have a car moving on a straight line, and even free falling object. So here in the 1D motion, we look at the motion of a particle along an horizontal straight line. It can be moving in both directions, this way or that way. And we look at the motion of an object along the vertical straight line, usually these bodies which are falling under the influence of gravity. And we can even look at the motion of an object along any general straight line. So these are the the broad examples of the one-dimensional motion. Talking about the two-dimensional motion, if the motion is confined to a plane, that is what we call as a two-dimensional motion. And when we talk about an object moving in a plane, we will be talking about both coordinates. Let us say for example, if an object is moving in the xy plane, then both the x coordinate value and y coordinate value, when it is moving from one place to other place, both the x coordinate value of the position changes as well as the y coordinate also will be changing. Examples are a circular motion, and also if you have a billiards ball, the balls will be moving on the billiards table. If you have a billiards ball, the balls will be moving on the billiards table. So this is also the example of a two-dimensional motion. The last one, which is the general type of motion, is a 3D motion, where the object will be moving in a space, and we see that all the three Cartesian coordinates, x coordinate, y coordinate, z coordinate, will be changing when it is moving from one place to other place. Examples are the motion of a flying kite, and a flying insect, or rather anything which is moving in space, we can take it as an three-dimensional motion. Now in the subsequent videos of this topic, we'll go and take a deeper look at how we'll study this one-dimensional motion.